Hello everyone. In this video, I am going to give a brief lecture about sequence and series concepts. It's from calculus main topic. In GATE examination, there are 17 branches as the engineering mathematics syllabus. A few branches do not mention this topic, but this is a common topic. So 17 branches also has the subtopic sequence and series. In particularly test for convergence of series. It is very important concept, test for convergence of series. Now I am going to give a only summary of sequence and series concept. In the forthcoming videos, I will give previous year questions related to this topic sequence and series. Next, I explain weightage of this topic sequence and series. Maximum 3 marks comes from calculus topics. In GATE examination, maximum 3 marks comes from calculus topic. This subtopic has low chance only. Only 5% of chances to get a question from this topic for all branches. Only 5% of chances to get a question from this topic. Now let's move on to the concept. This video is useful for all branches. Now let's move on to the concept. First, I explain what is sequence, the definition of sequence. A sequence can be thought of as a list of numbers written in a definite order. A1, A2, etc., An, etc. Here, A1 is the first term, A2 is the second term, and in general, An is the nth term. We will deal exclusively with infinite sequence, and so each term An will have a successor An plus 1. An plus 1. Here for every positive integer n, there is a corresponding number an. So a sequence can be defined as a function whose domain is the set of positive integers. A sequence can be defined as a function whose domain is the set of positive integers. We usually write an instead of the function notation f of n. An as the f of n. For the value of the function at the number n. Okay, this is for the value of the function at the number n. This is the definition of sequence. The sequence is denoted by set of all a1, a2, etc. It is also denoted by an. N equal to 1 to infinity also. This is the notation of sequence. Next, I will give some examples. Some sequence can be defined by giving formula for the nth term. In the following examples, we give 3 descriptions of the sequence. One by using the preceding notation, another by using the defining formula, and a third by writing out the terms of the sequence. Notice that n doesn't have to start at 1. It is very important. In the first example, set of all n by n plus 1, n equal to 1 to infinity. First I write this is n by n plus 1, n equal to 1 to infinity. This is preceding notation. Next, defining a formula an equal to n by n plus 1. The last method is write out the terms. The first term is n equal to 1, so substitute n equal to 1. I got the first term a1, that is 1 by 2. Second term is substitute n equal to 2. I got the a2, that is 2 by 3, 3 by 4, etc. and so on. That nth term is n by n plus 1 and so on. This is the infinite sequence. This is one example. Next, I am going to explain what is Fibonacci sequence. It is very important sequence, standard sequence, Fibonacci sequence. The Fibonacci sequence Fn is defined recursively by the condition f1 equal to 1, f2 equal to 1, fn equal to fn minus 1 plus fn minus 2, n greater than or equal to 3, n greater than or equal to 3. That means each term is the sum of the two preceding terms. So the first few terms are, first term is 1, second term is 1, third term is 1 plus 1, 2, fourth term is 1 plus 2, 3, fifth term is 2 plus 3, 5, and next term is 3 plus 5, 8, and etc. This is the Fibonacci sequence. These two are example of some sequence. Next example, find a formula for the general term an of the sequence. One sequence is given, we have to find the general term an. Here notice that the numerator of these fractions start with 3. The numerator of this fraction start with 3 and increase by 1 whenever we go to the next term. The second term has numerator 4, third term has numerator 5. So, in general, the nth term will have the numerator n plus 2 because here first term is 1 plus 2, second term is 2 plus 2, 3 plus 2, 4 plus 2, etc. So, the general nth term will have a numerator equal to n plus 2. Next, analyze the denominator. The denominator are the powers of 5. 5 power 1, 5 power 2, 5 power 3, etc. So the denominator is 5 power n. The signs of the terms are alternatively positive, negative. So we need to multiply the power of minus 1. So finally I got the nth term is minus 1 whole power n minus 1 n plus 2 by 5 power n. N minus 1 or n plus 1. These two are correct. So the nth term an equal to minus 1 whole power n minus 1 n plus 2 by 5 power n. The next definition is convergent and divergent of a sequence. A sequence set of all an has the limit L and we write limit n tends to infinity an equal to L or an tends to L as n tends to infinity. That means if we can make the terms an as close to L as we like by taking n sufficiently large. If limit n tends to infinity an exits, that value is L. So limit n tends to infinity an exits, we say that the sequence converges. Otherwise, we say that the sequence diverges. That means a sequence an is said to be convergent, then the limit exits. Limit means limit n tends to infinity an exits. Then the sequence is said to be converges. Otherwise, we say that the sequence diverges. This is the definition of convergent and sequence. Next, one example. We have to check is the sequence an equal to n by root 10 plus n convergent or divergent. Here I use the definition of convergent sequence. First I find the limit n tends to infinity an value, it is exists. Then the sequence is convergent, otherwise it is divergence. Okay, limit n tends to infinity an is n by root of 10 plus n. Here I write limit n tends to infinity. I write this n is 1 by n into root of 10 plus n. I take the 1 by n into square root. I got the value is 1 by root of 10 by n square plus n by n square, that is 1 by n. So finally I got this value is infinity because the numerator is constant and the denominator approaches to 0 because limit n tends to infinity 10 by n square is 0 plus limit n tends to infinity 1 by n also 0. 0 plus 0, 0, square root 0 is 0. So denominator approaches 0 but the numerator is constant. So the total values approaches 0. So the sequence, infinity. So the sequence an is divergent because limit n tends to infinity an does not exist. So the sequence an is divergent. This is the one example of how to check one sequence is convergent or divergent. This is the one example. Next, I am going to explain what is increasing and decreasing sequence. A sequence an is called increasing if an less than an minus 1 for all n greater than or equal to 1, that is a1 less than a2 less than etc a3 etc. Okay, this is this is wrong. An is less than an plus 1. Okay, a sequence an is called increasing if an less than an plus 1 for all n greater than or equal to 1. That means a1 less than a2 less than a3 less than etc. Suppose it is called decreasing. The sequence is called decreasing if an greater than an plus 1 for all n greater than or equal to 1. That means a1 greater than a2 greater than etc. So a sequence is monotonic if it is either increasing or decreasing, then the sequence is said to be monotonic. So finally, increasing sequence, it satisfies an less than an plus 1 for all n greater than or equal to 1. Decreasing sequence satisfies an greater than an plus 1 for all n greater than or equal to 1. A sequence is monotonic if it is either increasing or decreasing. This is the definition of increasing and decreasing sequence and monotonic sequence. Next definition. One definition is given, that is A sequence an is bounded above if there is a number m such that an less than or equal to m for all n greater than or equal to 1. It is bounded below if there is a number small m such that m is less than or equal to an for all n greater than or equal to 1. Here one n is made. Let's see, n greater than or equal to 1. If it is bounded above and below, then an is bounded sequence. If it is bounded above and below, then an is bounded sequence. This is the definition of bounded above, bounded below, and bounded sequence. Next is, what is series? What is series? Okay, add the terms. Suppose if in general, if we try to add the terms of infinite sequence n equal to 1 to infinity, we get an expression of the form a1 plus a2 plus etc. an plus etc., which is called an infinite series and is denoted by the simple sigma n equal to 1 to infinity an. This is the definition of series. That means if we try to add the term of an infinite sequence, we get an expression. That expression is called an infinite series. It is denoted by sigma n equal to 1 to infinity an. Next, what is convergent and divergent series? Given series is sigma n equal to 1 to infinity an, that is this one, let Sn denote its nth partial sum. That means Sn equal to sigma equal to 1 to n, sorry, not infinity, n ai a1 plus a2 plus etc. an. The sum of the nth term is called Sn. If the sequence Sn is convergent, that means limit n tends to infinity Sn equal to S exits. Limit n tends to infinity Sn exits as a real number, then the series sigma an is called convergent. Okay, so one series is convergent, then the nth partial sum Sn, the sequence Sn is convergent. That means convergent, what is the definition of convergent sequence? The limit exists. What is the limit? Limit n tends to infinity Sn exists as a real number. Then the series sigma an is called a convergent series. Okay, then that means we write a1 plus a2 plus etc. an. Also we write a1 is this is also small s, or sigma n equal to 1 to infinity an also yes. The limit is also the sum of the series. The number s is called the sum of the series. This s is called the sum of the series. Next, if the sequence Sn, that the partial sum, nth partial sum a1 plus a2 etc. an, the sequence Sn is divergent, then the series is called divergent. Okay, what is the sequence divergent? The limit does not exist. Limit exists, it is convergent. Limit does not exist, then it is called a divergent sequence. The sequence is divergent, then the series also divergent. This is the definition of convergent and divergent series. Next, I'm going to give us some standard series. You have to know what is geometric series, arithmetic series, and P series, etc. Here I give some standard series. It is very, very important and useful series. This geometric series, sigma n equal to 1 to infinity a r power n minus 1. This is the geometric series, a plus ar square, each term multiplied by r. Here the common ratio is r. Is convergent if modulus r is less than 1. Then only it is, the geometric series is convergent. It is convergent, then it is sum is sigma n equal to 1 to infinity a r power n minus 1 equal to a by 1 minus r. This is the formula for finding the sum of the geometric series. Suppose it is convergent, then only use the formula a by 1 minus r if modulus r less than 1. If modulus r is greater than or equal to 1, then the geometric series is divergent. So you doesn't know the sum, okay, because the series is divergent. So the geometric series convergent if modulus r less than 1 and divergent if modulus r greater than or equal to 1. This is the standard result or standard series. Here I give another one result, 1 plus 2r plus 3r square plus 4r cube plus etc. equal to 1 by 1 minus r whole square. This is very, very, very important result. Many questions were asked in the previous year questions by using that result. Okay, so this result is very, very important. Next result, If the series sigma n equal to 1 to infinity an is convergent, then the limit n tends to infinity an equal to 0. Then the series, here series, you have to notice this. Okay, series is convergent, then the nth term, limit n tends to infinity nth term an equal to 0. Then it is convergent. Okay, so the test for divergence gives if limit n tends to n tends to infinity an does not exist, or limit n tends to infinity an not equal to 0, then the series is divergent. It is very important test for divergence only. Okay, limit n tends to infinity an does not exist, or limit n tends to infinity an not equal to 0, then the series sigma n equal to 1 to infinity an is divergent. Okay, next, test for convergence of the series. Test for convergence of the series. In the next section, we discuss several tests that enable us to determine whether a series is convergent or divergent. Some tests are available, that is integral test, comparison test, and ratio test, root test, and etc. Okay, in the next section we will discuss several tests, that is, for I think there are 5 tests is available. I discuss these 5 tests only. Okay, the tests are useful to whether a series is convergent or divergent. Determine whether the series is convergent or divergent. The first one is integral test. Next I explain what is integrals test. Suppose f is a continuous positive decreasing function on the interval closed interval 1 comma infinity closed and open, and let an equal to f of n, then the series sigma n equal to 1 to infinity an is convergent if and only if the improper integral 1 to infinity f of x dx is convergent. That means first one I write the condition for convergent. If limit 1 tends to 1 to infinity f of x dx is convergent, then the series also convergent. Okay, the limit convergent, then the series also convergent. This is the definition of convergence. Sorry, integral test for convergence. Okay, next second one is I write the condition of divergent. Limit integral 1 to infinity f of x dx is divergent. This integral is divergent, then series also divergent. This is the integral test. You can use only f is continuous positive decreasing function, then only you can use the integral test. It is very important. F is a continuous positive decreasing function on that interval, then only you can use the integral test. What is it? Integral test? The integral is convergent, then the series is also convergent. Then integral is divergent, then the series also divergent. This is the integral test. Next, I will give an example for integral test. Test the series sigma n equal to 1 to infinity 1 by n square plus 1 for convergence or divergence. The function f of x, what is that function? An term is the function. That is, I write f of x equal to 1 by x square plus 1. Clearly, obviously, the function f of x is continuous, positive, and decreasing. You have to check these 3 conditions on that interval 1 comma infinity. Obviously, the function f of x is continuous, positive, decreasing on 1 comma infinity. So we use the integral test. First, you have to find the value of integral. That is, integral, the limit is 1 to infinity. So integral 1 to infinity f of x dx. What is f of x? Integral 1 to infinity f of x is 1 by x square plus 1 dx. So I write this is the improper integral. Limit t tends to infinity integral 1 to t 1 by x square plus 1 dx. What is the integration of 1 by x square plus 1? That is tan inverse x. That is tan inverse x. So limit t tends to infinity tan inverse x. The limit is 1 to t. Limit t tends to infinity. First I substitute the upper limit t, and next I substitute the lower limit 1. So finally I got limit t tends to infinity tan inverse of t minus tan inverse of 1 is pi by 4, that is tan pi by 4 is 1, and limit t tends to infinity, tan inverse of t is tan 90, that is 90 pi by 2, then only the value tan inverse t tends to infinity, tan inverse of x is pi by 2. So pi by 2 minus pi by 4, this is equal to pi by 4. Here the integral is convergent, that value is pi by 4. So the series also convergent. Series is convergent because the integral is convergent. This is one example. Next, I will give another one example. It is very important example. P series. Okay, this is called P series. When by using that example, you can say when will the series when will the P series is convergent and divergent. So this is very important example. First, for what values of P is the series is 1 by n power P convergent. Okay, I analyze some cases, values of P. Okay, first I take P less than 0. P less than 0, limit n tends to infinity 1 by n power P equal to infinity. This is the nth term, an. Limit n tends to infinity 1 by n power P is infinity because P is less than 0. So n power minus n power minus power. Okay, so in the denominator has nth minus powers, negative powers. In the denominator is minus power, then we got the numerator is positive, n tends to infinity, so this is infinity. If P equal to 0, next I analyze the case P equal to 0, then limit n tends to infinity 1 by n power P. P 0 means n power 0, this is 1, 1 by 1, 1. In either case, another case, limit n tends to infinity 1 by n power P not equal to 0. That means this is not equal to 0. Okay. So the given series diverges in these two conditions. P less than 0 and P equal to 0, the given series is diverges by using the test for divergence. What is the test for divergence? Limit n tends to infinity an not equal to 0 and this is equal to infinity, then the series is said to be divergence. In this case, this is true. Here P less than 0, that value is infinity. Nth term value, limit n tends to infinity, nth term is infinity. P equal to 0, 1 by n power is 1. This is not equal to 0. So by using the test for divergence, I can say if P less than 0 and P equal to 0, the series is divergence. Next, analyze the case P greater than 0. Okay. Here the function f of x equal to 1 by x power P is clearly, obviously this function is continuous, positive, decreasing on the interval 1 comma infinity, decreasing. Okay, 1 comma infinity. Here I analyze P greater than 0 is P equal to 1 first. I analyze P equal to 1. Integral 1 to infinity, P equal to 1 means 1 by x power P, P is 1, 1 by x dx. That means limit t tends to infinity, integral 1 to t. This is an improper integral, so I can write this one 1 by x dx. Integration of 1 by x is log x. Limit t tends to infinity, log x 1 to t. Here log t minus log 1 is 0, but log t as t tends to infinity, so finally I got log infinity is infinity. So limit t tends to infinity, log x value is infinity. This limit does not exist as a finite number. So by using the integral test, the improper integral 1 to infinity 1 by x dx is divergent. So the series is divergent is divergent. So the series also divergent at p equal to 1, and before I explain, series also divergent P less than 0 and P equal to 0. So here I write series divergent if P less than 0 and p equal to 0, and this is also true. The series is also divergent at p equal to 1 also. So next I analyze p greater than 1, that means p not equal to 1. Okay. So I assume p not equal to 1, then integral 1 to infinity 1 by x power p dx equal to limit t tends to infinity integral 1 to t 1 by x power p dx. The integration of 1 by x power p is x power minus p plus 1 divided by minus p plus 1 1 to t. So finally I write limit t tends to infinity. Here 1 minus p is constant, so I take it outside, and first I substitute the upper limit t, so I got 1 by t power 1 p minus 1. Okay, 1 by t power p minus 1, and I substitute the value of 1 power is 1 only, so minus 1. So here p greater than 1. Okay, p greater than 1, then p minus 1 is greater than 0, p minus 1 is greater than 0. So as t tends to infinity, t power minus 1 also tends to infinity. So t 1 by t power p minus 1 tends to 0. So finally this term is 0. Limit t tends to infinity 1 by t power minus 1 is 0. So finally I got minus 1 only. So multiply 1 by 1 minus p into minus p is 1 by p minus 1. So the integral is converges. The integral is converges if p greater than 1 and diverges if p less than or equal to 1. Finally, I write the integral 1 to infinity f of x dx is converges only at p greater than 1, diverges if p less than or equal to 1 also. Okay. So by using the integral test, the series is sigma. Here I write sigma 1 by n power p, n equal to 1 to infinity. The series is convergent if p greater than 1 and divergent if p less than or equal to 1. This is the final answer. This series is also called p series. Sigma 1 by n power p is also called p series. This is the two example of integral test. It is very important result. By using that example, you can say when will the p series is convergent and divergent. It is very important result. The p series is convergent if p greater than 1 and divergent if p less than or equal to 1. Friends, in this video I gave some important concept in sequence and series. The remaining concepts will be discussed in the part 2 video. See you in the part 2 video. Thank you. If you like this video, please like, share and subscribe my channel to encourage me. Thank you.